we do have a fundamental sort of pulse spreading phenomena occurring, and a good approximation is that the F3dB is approximately equal to 1 over 2 delta tau. Okay, that certainly is reminiscent of what we did here in our dispersion and pulse spreading slide, where we said that the maximum data rate, the maximum bit rate that we can transmit through the system is less than or equal to, is limited on the high side by 1 over 2 delta tau. It's the same quantity basically here that we're seeing. And what this means is that the 3 dB bandwidth is simply another way of characterizing the maximum data rate that our fiber optic system can take. Let me go ahead and show you the mathematical form that is typical here. Very typical, not only because it really does work in the real world, but because it's easy to deal with mathematically, is a Gaussian frequency response. Okay, and what we'll do is we'll write that A prime over A, this ratio, A prime, it's a function of frequency, is looking something like e to the minus alpha f squared, where alpha is a constant. And you can recognize this as a Gaussian. Okay, and instead of writing just alpha, we're going to go ahead and write e to the minus natural log of 2 f over f 3 dB quantity squared. And that way we have that A prime of f 3 dB all over A really is equal to 1/2. And you can do that calculation. And so that's what we want. What we're going to do is we're going to go ahead and convert this. Oh, okay, and so just to show you what this looks like, I'll make a quick plot of A prime over A as a function of frequency, and at 0 frequency. What we're going to have is we're going to have a Gaussian here. Okay. If we move this into a log coordinate, if we go ahead and convert this ratio into decibel units, A prime over A in decibel units. I'm running out of room here. It starts off, oh, let's see here, this is starting off at 1 because at 0 frequency we have A prime equal to A. We're assuming that this whole thing assumes that at 0 frequency we have the output amplitude equal to the input amplitude. That is at DC. We have 0 DC loss here in this system that we're looking at. This will start at 0 and we'll go down from there as a parabola. Okay, so this is a Gaussian and this is a parabola. But very often we'd rather go ahead and characterize this decibel ratio as a positive loss. And so what we're going to do is we're going to go ahead and for a realistic system we're going to characterize the loss as follows. We're going to write L is equal to total system loss, and we're going to break it into two pieces, L naught plus LF. And so this is the DC, or the fixed loss at DC, and this is our frequency dependent loss, which we just talked about. Okay, and so that frequency dependent loss is a function of frequency. So we got the subscript f, but it's also a function of f. And so what we're going to do is we're going to go ahead and calculate that as a positive value. We're going to use positive loss convention, so that, for example, 3 dB loss means that only half the power gets through the system, and we're going to say that the loss f as a function of f and in decibel units is equal to minus 10 log base 10 of a prime over a. Okay, and we can go ahead and make this calculation, noting that the log based a of x is equal to the log based b of x divided by the log based b of a. And so if we use this relationship, we can go ahead and calculate the loss f in dB units as minus 10 log 10 of e to the minus log 2, natural log of 2, f over f3 dB, quantity squared. The log of the exponential, we're going to go ahead and use that, this formula down here, and we're going to get minus 10 times the natural log of e to the minus natural log of 2 f over f3 dB squared divided by the natural log of 10, and that gives us 10 log of 2